Homework, we've got 2 assignments due this week, one on Wednesday and then one on Friday, okay? There's one problem on Friday's assignment, just so you know what not to do. It's problem 176, and it's going to be typical. There's a part A and part B. And under part B, there's a red box around the B. The red box means it's best solved using their particular heat transfer software that comes with the textbook. We're not going to work those. So if you see a red box around any part of a problem, ignore it. Don't do it, because you need to use their IHT heat transfer software to solve that. Okay. Now, I've put on the board a review of where we were last time. This was pretty much chapter 1 review, the equations. We start out with conduction, and that's Fourier's law. Q is called the heat rate. It's in watts, minus Ka dt dx. K, thermal conductivity. A, the area through which heat's transferred by conduction. The temperature gradient dt dx. In chapter 1, we're going to assume the temperature profile for conduction is linear. That won't happen in other chapters, but for chapter 1, we assume it's linear. If we assume it's linear, we can replace dt dx with delta T over L. This is the form of the equation we use pretty much in chapter 1. For our convection heat transfer, Newton's law of cooling. Q, the heat rate in watts. H, the convection heat transfer coefficient. By the way, K is a property of the material or substance, like air, water, steel. The values are in the back of the book, in the appendix. H, we have to find out how to calculate H pretty much in chapters 6, 7, and 8. It's not as easy as going to the back of the book in the appendix and finding H. You won't find them back there. A is the area that the fluid touches the surface. So this area is the area that the fluid touches the surface. If it's a sphere, the area of a sphere with air around it, pi d squared. If it's a pipe, pi d L. If it's a wall, like the back wall, the height of the wall times the length of the wall, where the fluid touches the surface. That's the area. Ts is the surface temperature, T infinity is the free stream temperature. For radiation, Stefan-Boltzmann law. Again, Q in watts, the heat rate. A constant, sigma, the area that's emitting the radiation, the emitting area. Surface temperature, raised to the 4th power. Surface temperature must be in absolute temperature. Convection, you can use absolute or relative. Conduction, absolute or relative. Radiation, only absolute. This is for a single surface emitting radiation. If we have 2 surfaces exchanging radiation, and one happens to be small in a large enclosure, then this is the correct equation right here. T subscript SURR is the surroundings temperature of the surface at temperature Ts. And we ended up last time with 2 energy balance equations, one for a control volume, E dot in minus E dot out plus E dot gen equal E dot storage. If we look at a surface and not a control volume, but a very small surface, the surface is infinitesimally thin, the volume approaches 0, the mass approaches 0, so there can be no storage, it goes to 0. There can't be any generation, it goes to 0. We're left with E dot in must equal E dot out. So pretty much those are the basic equations from chapter 1. There's one that I didn't put on the board last time on radiation. It's alpha is the absorptivity. Again, it's dimensionless. It's between 0 and 1. And it's pretty much what the name implies. It's the absorption of the radiation by the surface. The absorption of the radiation by the surface. So if a surface is black, alpha can be close to 1. If it's highly reflective, alpha can be a lot less than 1, close to 0. You buy a black car, you know on a hot day you're going to pay a price because touch the hood, touch the top. Black upholstery, same thing in your car. You want to build a good solar collector, don't paint it silver, paint it black. Why? You want a good absorption. You want alpha to be high for solar radiation to be absorbed on the surface. So again, it's a property of the surface. One of your problems for homework involves using alpha. So you take alpha times the solar radiation, watts per square meter, and that gives you how much is absorbed. Okay, and there's our Q's again, Q, Q prime, Q double prime. Q, it's called the heat rate, it's in watts. Q double prime is called the heat flux, it's in watts per square meter. Q prime is a no name, I'm not giving a name. It's the heat rate per length. That's what it really is, heat rate per length. So if they ask you for something that's a problem or give you something that's a problem with those units, then you know what you're supposed to find or what you're given, Q, Q prime, or Q double prime. All right, so with those, let's work some example problems out of chapter 1, similar to your problems for homework. The first one I'm going to work is problem 10. And for homework, you've got 6 and 7. So I'll work 110. Okay, 110, let me read it because these problems are pretty wordy and there's not always a lot of pictures with them. 110 is a freezer compartment, which is a cube, 2 meters on a side. So we've got a freezer compartment, 2 meters on a side. It's cubical. Looks like this. Okay, let's keep reading. Assume the bottom to be perfectly insulated. Perfectly insulated. Sometimes we call that adiabatic, of course. In thermal, adiabatic. So perfectly insulated. It's resting on the floor, so it's not going to lose much heat compared to the top, right side, left side, front and back. Okay, keep reading. We're going to apply styrofoam insulation on the outside of that freezer to insulate it, K.030. That's insulation. And he tells us also that the inner surface and outer surface are minus 10 and 35 degrees C. T inside the freezer, you want to be cold, minus 10 degrees C. The outside is wherever you're at with this freezer, in your garage, you know, in your house, somewhere else. That temperature is 35 degrees C. The heat load is 500 watts. Right. How thick must the insulation be? Okay. He didn't tell us air temperature. He didn't tell us the convection coefficient. So we're not supposed to be considering convection over there. He didn't tell us the emissivity of the insulation. He didn't tell us it's in a big room, so we're not supposed to use radiation. Well, left with what? Obviously, we're left with conduction. Okay, this is the conduction problem. And if you ever get confused, he's been really kind. Kind of, not always, but kind, sometimes kind. Homework problems, big red letters. Everything following here is conduction. Thank you very much. Okay. Big red letters. Convection, everything following here, use convection. And so on, all the way back. Energy balance, all these problems here. So you'll be led by the hand to know what to do. But that's good news, bad news. On an exam, I can't lead you by the hand. You have to know from what I give you where you want to go and how to get there. Okay, so that's why I'm mentioning there's no convection here, there's no radiation, because they didn't give us any information on that. All we know is conduction through what? The insulation. Okay, we slap insulation on 5 sides: the top, the front, the back, the right, the left. The bottom is adiabatic. No heat gets out, ignore it. There's the equation, chapter 1, Q equal Ka delta T over L. There it is, L. Find L. L equal Ka delta T over Q. K, styrofoam insulation, back of the book. 0.030 multiplied by A. Okay, what is there? There's a top, there's a left side, there's a right side, there's a front, there's a back. Yep. Are you officially in this section? Come over here, use this one here. So, five sides. Each side's 2 by 2. There's the, oops, wrong way. Let's put them right here. 5, 2 by 2. Okay, conduction. Hot side. Outside, 35 degrees. Cold side, inside, minus 10 degrees. 35 degrees outside is about 95 degrees, a hot day, Fahrenheit. So outside our freezer is 95 degrees Fahrenheit. The inside of the freezer, minus 10 degrees C, is 14 degrees Fahrenheit. So inside the freezer, 14 degrees Fahrenheit. Q, the conduction through the 5 walls. Q. He didn't say the heat transfer through the 5 walls. He said, how thick should the walls be to keep the heat load less than 500 watts? Well, you've got to kind of understand then what heat load is. If it's going to be Q, of course, it's going to be 500 watts. What is heat load? Okay, when you take ME418, you talk about HVAC systems and how to design them. And if that system went out in this room right now, no more air conditioning in the room, how much heat's being generated in this room? Well, we've got 35 people times so many, watts for each person putting out. So we've got the heat load of people. We've got the lights. And if we had 32 computers in here, the heat from the computers, and the heat that comes through the windows, pretty much the wall, the hall in here is the same temperature. The room over there is the same temperature as here. The room over here is the same temperature. So the heat comes from the outside if it's a hot day in here. You add all that together. That's the heat load. That means that HVAC system has to take out the heat from our bodies, from the lights, from the PCs, in order to keep the temperature in here from changing. Otherwise, this room gets hotter and hotter. As we know, it's classic on final exam week. You know, something goes out and this room gets about 95 degrees. Yeah, that's because we're not taking the heat out of here. So we're trying to keep this freezer inside cold. And, you know, if you take a styrofoam cooler out to the beach on a hot day, stuff inside is going to start to get warm. So how much heat do you have to take out of here to keep that temperature minus 10 when the outside's 95 degrees outside? The answer is 500 watts. How thick should the insulation be? Okay, anyway, 500 watts, got it. Okay, so L equals 0.054. 5.4 centimeters. Yep. About 2 inches. About 2 inches. So you slap 2 inches of insulation on that freezer. Okay. That's what the thickness of insulation would be there. All right. Only conduction. Let's try another one. Let's see here. Homework, you have 23. I'll do 21. 121. Okay, I'm going to read 121. There's no picture. Electric resistance heater is embedded in a long cylinder, 30 millimeters. Okay. 21, there it is. 30 millimeters in diameter. Okay. All right. And we're going to take it. Air flows over the cylinder 25 degrees C. So air flows over the cylinder . And the velocity of the air is 10 meters per second. Okay. You want to keep the surface temperature at 90 degrees C. Okay, the air is at 25. Okay. What should the value of H be? Okay, first of all, this is a solid cylinder originally, and then you drill a hole in it. Let's say the chalk is the electric resistance heater. The chalk's the heat. You can buy them. 2 little wires come out of here, hook the wires to a voltage supply, and this thing gets hot. Okay. So you drill a hole. It could be an aluminum cylinder. Drill a hole in the aluminum cylinder, insert the heater in there, and that's what they mean by a heater is embedded in a cylinder. So a cross section looks like this. This is the heater. This is the cylinder. Okay. So all the heat that comes out of the heater goes through the cylinder to the air. All the heat that comes out of the heater goes through the cylinder and ends up in the air. Okay. Air is cold. Cylinder is hot. Find H. Did they give me thermal conductivity? No. Is there anything about conduction here? Yeah, but it's we're not going to use anything. Radiation? No, it didn't say small object in a large room. It didn't give emissivity. It didn't say black surface. No. No radiation. No conduction. There it is. It's a convection problem. Okay, convection problem. Q equal H A T S minus T infinity. Supposed to find H. There it is right there, H. TS, surface temperature. Yeah, 90. Now I can put TS here. TS equal 90. Fluid temperature, free stream fluid temperature. Oh yeah, 25. Okay, he also told me, he said the heater puts out 400 watts per meter. Uh-oh, there's the magic words again. I told you, always look for the magic words. If they ask you for something, or if they give you something, you better know what they give you or what they're asking you to find. Q? No. Q double prime? No. Q prime? Of course. How do I know that? There it is, per meter. That's why. What does that mean? That means I divide both sides of the equation by the length. Okay. Q prime equal Q over L equal H. The area pi d L divided by L T S minus T infinity. L cancels. I'm supposed to find H. Okay, H equal Q prime divided by pi d Ts minus T infinity. Okay, H's, L's cancel out. Da 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 da. Yep, pi dl. Okay. Okay, Q prime. 400 watts divided by pi, dimensionless. Diameter given 30 millimeters. Ts given 90. T infinity given 25. $65 watts per meter squared K. All right. The velocity of the air, 10 meters per second. I don't care. I didn't use it. It's just there for flack. You know, he just put in the problem. You don't use it ever. Oh, you will in chapter 6, 7, and 8, because the next question is it, you know, maybe, for instance, if it's a flat plate, is it laminar or turbulent? Is there a wake region? Where's the separation point over a cylinder? But in chapter 1, no, we don't need it. He put it in there, but we don't need it, but we will in chapter 6, 7, and 8. Okay, just so you know, not needed. Let's put the units in, because it's very important. K, watts per meter. K. Area, meters, 2 meters times meters. Degree C, watts. Start counting things out. Watts, meter, meter. Okay, I want L to be in meters. Watts, dimensionless. D, meters.
Oh.
Degree C.
I think your Q prime should be 400 watts per meter.
Yeah, thank you. Watts per meter squared, degree C. Meters times degree C divided by degrees K. What in the heck is that? How can the length of the thickness of a wall be in meters, degree C per degree K? That's nonsensical. Of course it is. Of course it is. And the reason is because, you know what? I don't like that degree C there. I'm going to make that degrees K. cancel, cancel. Okay, it's fine now. You know what? I don't like that degree C there. I'm going to make that degree K. Drive some people crazy. Say, whoa, 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 you can't do stuff like that. Don't you have to add 273 to degree C to get degree K? Well, if you give me a temperature in degree C, I do. But if you give me a temperature difference, I don't. Boiling point of water. Freezing point of water. Freezing point of water. Boiling point of water. Wow, isn't that interesting? It doesn't make any difference. And why? Because you see the minus sign. As long as you subtract, doesn't make any difference. If you don't like degree C over here, you make it degree K, because it doesn't make any difference. Why? Well, you know, it's pretty simple to figure out. 35 plus 273 minus a minus 10 plus 273. All right, let's see what happens here. Plus 273 minus 273. Gone, gone. It makes no difference. Makes no difference. So don't get confused about that, okay? As long as there's a difference, you can use either degree C or degree K. Okay, so that's why the answer is in degree K, even though this was in degree C, okay? All right, let's do another one. Okay, I'll put it right here. We won't need this anymore. All right, let's try this one. Yep. 31. You have problem 30 for homework, I'll do 31. Okay, we have a spherical instrumentation package. Spherical. It's in a space simulation chamber. So it's in a space simulation chamber. Okay, the walls of the chamber are at 77 absolute. The walls are the surroundings. The spherical instrumentation package is in the room where the walls surround it. Diameter is 100 millimeters. Emissivity of the instrumentation package is 0.25. Now, this is a space simulation chamber, so there's no air in it. It's a vacuum, okay? If it's a vacuum, there's not going to be any conduction, there's not going to be any convection. This is a radiation problem, okay. The surface temperature, we want to keep it at 40 degrees C. If it's above 40 degrees C, the electronics start to malfunction. So to keep electronics happy, keep the temperature down to 40 degrees C. How much power can this dissipate in the chamber? So find the power dissipation. Okay, so we know that it's radiation. It's not a single surface. There's the instrumentation package and there's the simulation chamber. Okay, it's two surfaces. There it is, Q equal sigma epsilon A T S to the fourth minus T surroundings to the fourth. there's the power dissipation, which is Q. That's it. It's going to be in watts. Okay, sigma, 5.67 times 10 to the minus 8th. Epsilon, given to me, 0.25. Area of a sphere, pi d squared. D, 100 millimeters. Ts to the 4th. Uh-oh, watch out. These guys are going to be tricky. Degree C, degree K. This is radiation. Everything's got to be in K. So 40 plus 273. The 4th. Minus, this is in degrees K, 77 to the 4th. 4.3, a measly 4.3 watts. So if that instrumentation package generates any more than 4.3 watts, it's going to go above 40 degrees, and electronics start to fail. Did the problem say small object in a large enclosure? I'll read it again. An instrumentation package is placed in a large space simulation chamber. Oh yeah, there's the magic word, large space simulation chamber. Okay, yeah.
Is it always going to be discretely stated, or is it up to subjectivity and certainty?
In chapter 1, it's always, if there's two objects, one's going to be small and one will be large. So
right,
in chapter 1, it's pretty straightforward.
Okay.
Back in chapter 12 and 13, pretty much in chapter 13, yes, it is. It's much more difficult when they're not, but we'll do it in chapter 13. We'll do it in chapter 13.
All right, okay.
Yeah. As a matter of fact, we'll derive this guy, this one, in chapter 13. In chapter 13, yeah. So for right now, chapter 1, yes. Chapter 13, radiation heat transfer, no, it's not always small and large. Yeah. Like, put a baseball inside of a basketball. Is that small and large? Oh, no. No. Put a pea inside a basketball. Oh, yeah. Yeah, but, so don't worry about it in chapter 1, okay? It'll always be that equation over there.
Okay.
He's pretty good about it, too. He'll either say a small object or a large enclosure, or he'll say both, but normally just one he'll tell you.
Okay.
Yeah. Okay, now let's look at, this one was in the previous edition of the textbook, but I like it. Yeah, go ahead, I'm sorry.
Is the sigma always that number?
Yes, it is. It's in chapter 1 in the radiation part. It's in there. Yeah, it's a big, it's a small number. See that minus guy right there? This guy here, he's big. He's very small. So multiply small by a big and you get something reasonable. Okay, this problem was in the previous edition, but I like it, so I want to use this problem and show you what it's trying to show us here. Okay, this is an example problem. It's a long rod. And let me read it because this isn't a complete statement of the problem. Oh, I can't read it because it's not in there. Okay. It's conducting 4 amps of current. So the amperage through this rod is 4. Current I, not A. The resistance of the rod electrical resistance of the rod is given 0.4 ohms per meter. Okay, it's in a location where there's airflow over it. The temperature of the air is 300 K. And the convection coefficient is 100. It's in a large room whose walls are kept at 300 K. So it's like this room here. The air in this room is pretty close to the temperature of the walls in this room. Okay, so we have the current going through the wire, current I. It's a solid rod. I think that's all. Oh yeah, the diameter, yeah. The diameter of the rod is 1 millimeter. It's more like a wire. Find the surface temperature of the rod. Okay, so we're putting a current through a rod. It's in a room, a large room, which of course, since he gave us emissivity and he gave us the surroundings temperature, we know we're supposed to include radiation. Since he gave us T infinity, he gave us H, we know we're supposed to include convection.
What was the emissivity?
Sorry about that. 0.8, thank you. Yeah, let's put it right here. I'll put it up here. Thanks. Okay. No, yes, yes. All right, but this is called a combo type problem. We have two modes of heat transfer, and we need to do an energy balance. So I'm going to call, of course, my control volume the rod. That makes sense. So here's my control volume. Here's my equation. I'll write it down. E dot in minus E dot out plus E dot gen equal E dot storage. Okay. You have to make some assumptions. So we assume a steady state. I don't think he said that. Oh, it's the one in the book. He didn't say that. Want to read? Yeah, no, he didn't say that. So kind of here's the rule. Unless somebody specifically mentions a time variation of something, it's okay to assume steady state. But if you see time mentioned anywhere in that problem, it's probably going to be a transient problem. This is steady state. If it's steady state, there will be no change in storage. And E dot storage is the change in stored energy inside the control volume. Okay. When you pass a current through that rod, the rod gets hot. Your toaster. It glows red sometimes inside. Look inside of it. You'll see the little wires glowing red. Oh, it gets hot. That's pretty cool. That's room temperature. That's pretty cool. That's room temperature. The rod is hot. Energy goes out by convection. Energy goes out by radiation. Out. I said out 2 times. I didn't say in. Energy coming in? Oh no, 0. Energy going out. Okay, let's do them one at a time. Convection first. HA T surface minus T infinity. Radiation minus epsilon sigma A T surface to the fourth, T surroundings to the fourth. Plus E dot gen. Oh, the wire generates some energy. Yeah, I squared R, power is I squared R. So I squared R, and that's equal to 0. Okay. The rod's diameter, 1 millimeter. The length of the rod, if you read the problem, you say, I don't know, he didn't give me a length. No, but the problem probably says a long rod. Oh, a long rod, I don't know the length. I think I better do it this way. Of course, that's why the magic word helps you. The magic word is long rod. That means base everything on a per meter basis. That means divide the whole equation by the arbitrary length L. Divide it by an arbitrary length L. Look at this resistance. Is it in ohms? Because I'll tell you something, this R is in ohms. No, it's not in ohms. It's an R prime, ohms per meter. So, this term here, I squared R prime. 0.4 goes right there. Okay, this is a cylinder. What surface is touching the air? Because that area is the area that's this air touches the cylinder. Pi dl. Pi dl. That area then is pi dl. That area here is pi dl. Divide it by L. Cancels, 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 cancels. Okay. H pi d Ts minus T infinity plus epsilon sigma, I need more room here, epsilon sigma d Ts to the fourth, T surroundings to the fourth equal I squared R prime.
That was a pi then, right?
Oh, where is it? Oh, yeah, thanks. Thank you. Okay, don't forget the rule now. If a problem involves radiation, every temperature has to be an absolute. Every temperature has to be absolute. I don't care if it's conduction or convection or radiation, but every temperature has to be absolute. 300 K. Okay. So, do I know H? Yeah, 100. Pi D Ts, I don't know it. T infinity, 300. Epsilon, 0.8. Diameter, 1/10. Pi sigma 5.67, 10 to the minus 8, Ts to the fourth, minus 300 to the fourth, equal I squared, 4 squared, 0.4, R sub E prime. Solve for Ts. Ts comes out to be 63.5 degrees C. You have to change it to degrees C, subtract off 273. The answer will come out to be in K, of course, So then subtract 273 to get the answer in degree C. It's fourth order equation in TS, you have the software. Okay, so we did a control volume of the wire.
Why do you put it diameter is 0.1?
Oh, was it 1 millimeter? Good, I'm glad you caught me there. I think because I was on the last problem I worked, which was 1. Thank you. The answer didn't change.
What happened to the L underneath the I squared R?
Pardon me, say again?
What happened to the L?
Oh, he's lumped into it. R prime equal R over L. So take that R, E right there. Yeah. Not good for that. Okay, so over here we did a conduction, convection, radiation, control volume. Last one at the bottom, surface energy. All right, that's going to be a problem out of our textbook. 78, yeah, 178. Let's see, yeah, this is good. Okay, this is, okay, I'm going to try and draw, this is some kind of a duct carrying air. Let's just make it, here's air. On the bottom of this duct carrying air, we put a heater. We're trying to heat the air. So we put an electric heater on the backside. And I'm going to take, here's the wall, the bottom wall of the duct. This is the duct. This is the wall. Luckily, there's a picture in the textbook, so you can see what it is, the wall and that. Air flows inside the duct. The air is being heated by an electric heater on the bottom. So now I'm going to show the wall on the bottom here. So here's the wall. We're going to heat the bottom with an electrical heater, which we call Q naught double prime. And the air is flowing over the top of the wall inside the duct. So let's see where that is. There it is. 10 millimeters thick. This is 10 millimeters. Okay, the temperature of the air is given and the convection coefficient for the air is given. 30 degrees C, 100. 30 degrees C and 100 watts per square meter. Okay, okay, that's given. Duct wall. Okay, what else? Oh, okay. The top surface is to be kept at 85 degrees. So the top surface is to be kept at 85 degrees. Degrees C. Yeah. Oh, and K for the duct wall is 20 watts per meter K. Okay. Okay. Find, number one, find how much heat this electric heater has to put out. So part A, find how much heat the heater has to put out. And part B is find the temperature at the bottom, which is called T naught. Okay, T naught, and find T naught. Make sure the heater doesn't get too hot and burn out. Okay, so we've got something like a heating duct, a rectangular duct. Air is blowing inside the duct. We want to heat the air. On the bottom of the duct, we put like a little heater blanket on it. You can buy them. You put a current through it, a voltage across it, and you create heat. That heat is going to go up into the air in the duct and heat the air in the duct. Okay, we don't know how big the duct is. We have no dimensions, no height, no length, no width. So everything is based on a per unit area. There. Everything is based on watts per square meter. We want to know then how many watts per square meter are put in on the bottom of the duct. Okay. Well, we'll start off like we do over here. Okay. Draw a control volume around what's interesting to you. The wall's interesting to me. Everything inside the dashed lines is the control volume. The dashed line is the control surface. There's the equation. Okay. Energy balance. Okay. You know what? I'm going to do it over here because I need more space. Okay. Okay, now, so let's start back over here again. There's my control volume. It's a steady state. Problem. Didn't say anything about that. Okay, you heard my rule. If they don't mention time in the problem, you're allowed to say it. I think it's going to be steady state. So one of your assumptions is steady state. Okay. No change in stored energy. Is the bottom wall generating any energy by nuclear reaction or by whatever? No, no. Anything coming in, crossing the dashed line? Oh yeah, from the bottom, Q naught double prime, that comes in. Anything going out? Oh yeah, the top. Is there radiation from there to the walls of the top of the side walls of the duct? No, we're going to neglect it. Assumption is neglect radiation. Okay. So what's in there? Convection, right. H. Divide by the area because I want everything in double prime. I don't know the area. Okay. H. T hot. T hot is T top. Minus the air temperature, colder, T infinity. Yeah. Okay, this is energy balance on the control volume. Is Q naught in there? Yeah, it's right there. Do I know H? Yeah, I know H. 100. Do I know T top? Yeah, 85. T infinity? Yeah, 30. Use this to get Q naught. Okay. Well, find part A. I got to do part B now. Find T naught. Was it in the equation? No, I don't see it anywhere in the equation. Where is it? It's on the bottom surface. Oh, on the bottom surface. There's the magic word, surface. Yeah, right there. Control volume is bottom surface. Energy balance. On bottom surface. Okay, E dot in equal E dot out. What comes in? Okay, from the source, from the heater, electric heater, Q naught double prime. What's going out from the surface? Oh, conduction into the wall. Right, conduction into the wall. There it is up there. And there's the equation, chapter 1 right there. Get rid of the A. K delta T over L. What is delta T? Hot minus cold. This is hot, the top is colder. Okay, heat's going this way. T naught minus T top. Do I know K? Yeah, I know K. It's 20. Do I know T naught? No, I'm solving for that. Do I know T top? Yeah, 85. Do I know L? Sure, it's 10 millimeters. So, do I know Q naught double prime? Yeah, right here. I got it from part A. Part A. Solve this for T naught. Okay. Now, let's say that you see. You know what? I'm gonna try an energy balance on top. Why not? Okay, on the top surface, here it is up here, top surface. What comes in? Conduction through the wall. Okay, conduction through the wall, right there. E dot in equal E dot out. Conduction through the wall, K T naught minus T top. Okay, divided by L. And that's equal to here it comes in here. What goes out? Convection, that's right there. H T top minus T infinity. Let's see what I know. I know K, I know L, I know T top 85, I know H 100, I know T top 85, I know T infinity 30. Yeah, I could use this to get T naught. I could use this to get T naught. It would work, it would work. But if you start out, if you just start out and you don't do this, and you don't do this, and you just write this guy down, the first equation you write down, I don't know T naught, I don't know Q naught. Can't solve it, can't solve it. Are they independent? Let's see. If I put this Q naught right here, if I put this Q naught up here, that's equal to K T naught minus T top divided by L. Those two guys right there. Same. Nope. Not independent. Nope, 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 nope. There's three equations, but they're not independent. There's only two independent equations, which means you can only solve for two unknowns. Guess how many unknowns you have to find? Two. That's why. Three equations. But my point is, if you get into an exam where you say, gee, I don't see this problem, I don't know what's going on here, one of the things you should try is to put down on the paper equations you think might work. that might work. And look at them for a minute or two. Just stare at them. Think, what do I know? What don't I know? What am I supposed to find? And usually something will jump out to get you started, because if you write this one down first, and you say, that's not going to work. One equation, two unknowns. Well, then write the other surface down. Oh, yeah, I'll use this one. I'll solve for T naught. Then I'll use this one, and I'll solve for Q naught. So write the stuff down and look at it during an exam when your mind's under stress. That helps you get started on some problems sometimes. So, in conclusion, we've worked one of these guys, one of these guys, one of these guys, one of these guys, and one of these guys. We've worked one of each of those on the right-hand side of the board. Okay, the last thing, if you have your form filled out and didn't turn in yet, I need to give these to our department chair today. So give me your signed form for videotape.